So this first one, sine x, and just so we're clear, when you see this, cosine squared x, what does that mean? What does that mean? Cosine squared x. It means you do the cosine, and then you square it. That's what that means. This notation, throwing the 2 on the cosine before the x, it means this, and that's what you have to think. That's a lot easier to see it this way. Which technique? Chain. Undoing chains. Why? Sine x is essentially the derivative of the interior. So this is a chain rule derivative, right? This is multiplied by the derivative of the inside. There it is. Multiplied by the derivative of the inside. So now we're going to undo that. Okay? This one, cosine x times x squared. That's one of our common forms of undoing product. How many times will we have to do it? Yeah, there'll be 2 iterations of undoing product rule in there, okay? Arctangent 3x. One of the common forms of undoing product. So the common mistake here is to say that's a trig, like a more complicated trig. You don't use the trig identities. You undo the product rule for the inverse trig functions. So remember that. Okay, x e to the x squared. Chain, look, x is essentially the derivative of x squared. Undo the chain rule. Sine cubed x. Sine cubed x. This is trig. We're going to use trig to do this. And remember what we do, let's do this one. What we do in these is we stage it, so we use a trig identity to make it either simple, straightforward, or we're staging it, getting it ready for undoing the chain rule. So, if we were getting this ready for undoing the chain rule, we're looking to have something like this. A trig identity to some power times the derivative of that. And it doesn't matter what the power is, right? This can be any power, and we can easily undo the chain rule with that, right? Just raise the power. 1 over n plus 1, f of x to the n plus 1. So, staging for the chain rule means pulling away one derivative. Pulling away one derivative. So, what are we going to pull away here? What are we going to think about? What will our f be and our f prime in this case? So really I'm just dealing with 2 functions here. What functions am I dealing with? Sine and cosine, right? Sine and cosine. If I pull away one sine, I'm looking for then powers of what? Powers of cosine inside, right? But I've got sine squared. So if I can change that sine squared into any power or sum of powers of cosine, then I've got it because sine is my f prime, derivative of cosine to any power. Does this make sense? So how do I change sine squared into powers of cosine? So there's the Pythagorean identity says that sine squared equals 1 minus cosine squared. So now, sine x times 1, that's really easy. Sine x times cosine squared, there's the chain rule. In fact, that's the very first one up here. So that's how this works. You're trying to set this up so you have one trig function or sum of trig functions to any power times the derivative of that trig function. That's the chain rule. That's setting up for the chain rule right there. And then you can undo it. So I'm going to have antiderivative of sine minus antiderivative of sine times cosine squared, which is undoing the chain rule. Be 1/3 cosine cubed. And then you'll have a negative, right? 1/3 cosine cubed and a negative. Okay, last one. Sine x times cosine 2x. Another trig. This is definitely trig. And here's the problem with this one. I've got an argument of x and then a different angle measure argument. You really won't be able to unlock that until you get them all with the same argument. So you're going to use an identity for cosine 2x. Start with an identity for cosine 2x. And then all your arguments will just be x. And then you can make progress. All right, questions on the quiz? Yes, please.
How do you think would be the easiest way to differentiate product and chain? Because I think that's my biggest issue. I struggle differentiating both of them.
Okay, so I gave you the list of the common forms that would be for undoing the product rule. And those common forms, they don't fit the bill for undoing the chain rule. What is the requirement for undoing the chain rule? It's this very key thing. So when you do a chain rule derivative, it looks like this. So this is the pattern we're looking for if it's going to be undoing chain rule. And here's the key. You have the derivative of the interior of the other. Remember when you do the chain rule, you say take times the derivative of the inside. That's what you're looking for. Times the derivative of the inside. That's what you have to have for undoing the chain rule. You have to have that requirement met. With undoing the product rule, I gave you the list of common forms. None of those forms meet this requirement, right? So it's like a power, x to a power times cosine. So what would this need to be? How would you need to change this? So it would be undoing the chain rule. How would you need to change that one? Cosine x times x squared. So it would be undoing the chain rule. What small revision could you make? It's a great question to ask because it really sees if you can identify that and get it. Some people are saying change an x. So change which x? Change this x or this one? First or second? Change the first and make it cubed. If it was cosine of x cubed, look, here's the derivative of the inside. Derivative of the inside. X squared is essentially the derivative of x cubed. So if it were cosine x cubed times x squared, that'd be undoing the chain rule. But the way it stands, it does not fit undoing the chain rule, and it's one of our common forms for undoing the product rule. Is it better? Cool. Practice, right? So you got the 2-page worksheet of practice, and then the online practice problems are all really good. And in terms of these ones that aren't basic, straightforward, just quick, easy derivative rule, always look for undoing the chain rule first. That's always the first thing you look for. Undoing the chain rule. This pattern. Multiplied by the derivative of the inside. Multiplied by the derivative of the inside. That's the chain rule. We're going to undo that. Okay. So let's learn one more technique today. So here's a new one. Okay, so here we come to this one, and we say, is it simple and straightforward? Is there some function whose derivative is that? No, right? That's pretty complicated. And so then we ask, is it undoing the chain rule? Is it undoing the chain rule? Well, multiply by the derivative. Is this the derivative of this down here? No, right? You'd have two terms. If this were up here, you'd need two terms because there's two parts of the derivative. So it's not undoing the chain rule. Is it one of our common forms for undoing the product rule? Definitely not. Okay, that's not one of our common forms. It's not trig. Okay, so the only thing left is partial fractions. Is it partial fractions? Well, if you have good insight, you can kind of see that that's what's going on here. But what's the obstacle here? Why is it not exactly what we said? All these exponential functions, right? So there's something we can do to kind of take the exponential functions kind of out of our way for a moment to see this as a partial fractions problem, and that is what's called make a substitution or change of variables. And so often u is what's used for this, but you can use any variable that you want. And so the substitution I'm going to make is I'm going to say that u equals e to the x. So then what would e, so I've got e to the x, so that would be u. What would e to the 2x be? That would just be u squared, right? Okay, and so then the last thing I need to, I'm going to, when I switch it from x into variable u, I need to know what this dx is. Okay, so here's where we can use our rate of change. What is the rate of change of e to the x? E to the x. And what does that mean? What does it mean that the rate of change is e to the x? Who remembers? I promised you I'd be asking you this all semester. What does it mean that the rate of change is e to the x? I'll give you the first word. Given. Tia knows. Who else knows? Given. Yeah. Yeah. What's the meaning of that e to the x is the rate of change? E to the x is the rate of change. Tia, the only one? Go, Tia.
It's like the dy equals mdx.
Okay, so given what?
Given any change in the x, you get du for this one, or is it?
Okay, so you got the right idea. Given any small change in x, what can we determine then? The amount that u would change would be the rate times that change in x. Remember? This is our meaning for rate of change. Given any change in the independent, the corresponding change in the dependent variable will be the rate times the change in x. Still not there yet. We'll keep working on it. We're going to get it by the end of the semester. That's the meaning of rate of change. Given any change in your independent variable, the dependent variable changes by the rate times as much as your chosen change in the independent. Okay, so that helps us get what dx is. What is dx? Dx will be du over, okay, but what's e to the x? U. That's what we said. So that tells us what dx is. So dx is not just du. It's du over u, according to how I made my initial substitution. So now we're ready to, we can change this into make a change of variable from x to u. So the numerator will be u squared. E to the 2x will be u squared. And we got another u squared down here, plus 3u plus 2 times du over u. What happens to this u here? It just gets multiplied into our rate function, right? So in terms of the function u, this u in the denominator is part of the rate function. So I make a simplification. I got u squared on the top and u in the bottom, which gives me 1u on the top. What if there was no u squared up here? What if it's just like a number, like 4? What would happen to this u? It would get multiplied into the denominator, right? It wouldn't cancel out. So you just got to do the math right. It's not this. The pattern that you're seeing in this problem is not going to be exactly the same for every problem. You just do the math, do the algebra right. So in this case, we already had a u in the numerator that it could cancel out with. But without that, it would hook up with the denominator. Okay, so here we go. Now, what's that? So here's our side work, our intro work. What do we got? U over u squared plus 3u plus 2. Partial fractions. Conditions. Is the numerator degree less than denominator? Yeah, degree is 1, degree is 2. Okay? And then, can the denominator be factored? Those are our two conditions. Can it? U plus So we got one of the more basic ones here. We want to write that as the sum of fractions. Both of these are linear denominators, so we'll just have a constant. Constants in the numerators. Multiply top and bottom by u plus 1, right? Multiply top and bottom plus u plus 2 to get the common denominator. So we'll have a times u plus 1, b times u plus 2 equals, that numerator will equal u, right? It's got to equal what we started with. Stop me if I lose you, but hopefully you're gotten going on the homework, so this is familiar. So we'll have AU plus A plus BU plus 2B equals U. So then it looks like A plus B will be 1. A plus 2B will be 0. Easiest technique here is to subtract equations, do elimination, eliminate A. So it looks like I got negative B equals 1. Or B equals negative 1, A equals 2. So B is negative 1, A is 2. So I have 2 over U plus 2 minus 1 over U plus 1. And now I'm ready to, now I've got this as the partial fractions, which I can do antiderivative. And what's the key to these antiderivatives here? Natural log. Absolute value. And why is it natural log? So are they always natural log when you get done with partial fractions? So why are these natural log? It's the power in the denominator. What's the power in the denominator? 1, right? So this is like to the negative 1 power. Any other power is not natural log. Just because you got something in the denominator doesn't mean you're going to do natural log every time. It's only if it's to the first power in the denominator. Any other power is power rule, okay? Are we done? Why not? Okay, so our problem was to this problem in terms of x. So I have the antiderivative, the closed form, but in terms of u. So I need to once I've done the step of actually getting the closed form in terms of u, then I get the closed form in terms of x, which will be natural log of u dx plus 2 minus but we need all closed form accumulation functions that have this rate, which means why are there more than one? Why is there more than one accumulation function that has that original rate function? Because of the a value, where you start accumulating from, right? Because we can choose any a value to start accumulating from. So that plus c is the minus f of a from the fundamental theorem. Because we can start accumulating from negative 1 or 3 or 6. And those are all different net accumulation functions, but they have the same rate. They all have this rate. Okay, so questions on this? Change of variables. Please.
Shouldn't you have a 2 on the coefficient for your first term?
Yes, right, I forgot that. This should be a 2 right there. I just forgot that coefficient, so then there's a 2 here. I should give extra credit for catching a mistake, because then you guys would actually watch it and speak up. All right, questions on this example? Let's do another one. Well, that's not clear at all. That's better. Okay, so first question we ask, is it undoing the chain rule? So I want everyone to think about what small change to this would have to happen in order for this to be undoing the chain rule. Everybody think about that. What small change to this function could you make so that then your rate function would be a chain rule rate function? Everyone think about that. I'm going to call on somebody. Sage. What's that? Yeah, so if you got rid of the y, certainly, but that would almost not be chain rule at all. Then it would just be like power rule. So how could we keep both terms? What small change could we make in keeping both terms so then it would be undoing the chain rule? Yeah.
Y squared minus
In the inside?
inside.
He wants y squared on the inside. Right. Y squared means that then this is like times the derivative of the inside. Chain rule, times the derivative of the inside. If this were a y squared. It'd have to be power 2, though, because this is power 1. Okay, good. But that's not the problem we have. We have this one. And so we go through our techniques. Certainly not trig. It's not partial fractions, certainly. So what about product rule? Undoing the product rule. Well, maybe it kind of it has two factors. We might be able to do it with undoing the product rule, but it's not one of the common forms. Okay, so it's not one of the common forms. And so, as you suspect, this is a chance for substitution. So what should we substitute? U is what? So the thing that's kind of holding us back here and making progress with this is the fact that you have a y minus 8 under the cube root. So it'd be nicer just to have a single variable there. So we'll make u equal to the y minus 8. Okay, that means we need to know what y is. What is y? U plus 8. We also need to know what dy is. All right, so take the rate of change of this. Rate of change of that is 1. And what does the rate of change in 1 mean? It means given any change in u, the change in y would be 1 times that change in u. So there's my dy. Now we're ready to set it up. So we got y we said was u plus 8 times cube root of just u now. Dy equals. So in this case, dy is du, but that's not always the case. You have to chase it out. But in this case, dy is equal to du. Okay, did it help? Can we do something with this? Alex says yes. What could we do to continue to make progress now? You see, this is just u to the 1/3, right? And I got u plus 8 to the first, so just distribute. So I can distribute u to the 1/3 times u to the 1/3 times 8. Those are both pretty just straightforward power rule. So I'll have u to the 4/3 plus 8 times home free, right? Home free in terms of u. And then we just got to switch it back to y. Antiderivative of u to the 4/3. Raymond? Yep. Times 3/7 u to the 7/3 plus 8 times 3/4. And then, are we done? Change it back to y, right? So u is equal to y minus 8. I think this is 6. All right, plus c. So now I want to point out one thing here. Suppose we had a particular net accumulation function, for instance, from 5 to, let's say from 5 to y, and then this would be t's, right? T times 8 dt. Okay, so that would be the same thing, same problem we were given, but now I'm saying specifically we're going to start accumulating at 5, right? Same problem, but just a specific net accumulation function, the one that starts accumulating at y equals 5. Okay, so then what would that mean? So I come down to here. Actually, it's got to be actually a totally definite. So say I want the net accumulation from 5 to 9. So now this is not a function anymore. It's a number. It's an amount of change. It's an amount of accumulation as y goes from 5 to 9. So how would I do that? So I could come back down to here. I've got my what? I've got my net accumulation, or I got my closed form, and I would do what? I would evaluate that thing at 9 and at 5 and subtract, and that would give me a number, and that number would be the net accumulation from 5 to 9 accumulating at this rate. Okay, but what else could I do? So I could come here instead. Would I evaluate from 5 to 9? No, so when y is 5, what is u? -3. And when y is 9, what is u? So in terms of this variable, if I were to evaluate from 1 to -3, that would be the same thing as evaluating in terms of y from 5 to 9. So if you have a definite integral, if you're actually calculating an amount of accumulation, you don't have to change it back into the old variable. You could change the limits into the new variable. See that? So you can change the limits of integration from the y values into the u values and then get the value that way. Or you could switch back to the original variable and use the original limits. But those two expressions are equal. And then when you're actually evaluating a definite integral, the c goes away, right? Because it's going to be plus c minus c. So in a definite integral, you don't need the plus c because you're accumulating from there to there, and you don't have to worry about a minus f of a. Okay, questions on that? Please. Yeah, extra credit. Right? So because the y equals 5, that's my u is -3. And y equals 9, that's my u equals 1. All right, thank you. Good job. Any questions? Yeah. So if y equals u plus 8, so what's the derivative of u plus 8? This is the 1 from the u. Okay, yeah. Other questions? Okay, practice. We got some practice problems. Somewhere? Right there? Those big enough? Make it bigger? So I would say let's do the second one is similar to the one I just did. So let's make some progress on the first one and the third one. Okay, so I got most of the way done on that first one. And this will be in the video if you don't have time to process all that. But those who made progress, do you agree with this? Did I make a mistake somewhere? X is going to be 2 times u minus 1. That goes here. U goes under the radical. Then I multiply that out. I get 4u squared minus 12u plus 9 over u to the 1/2. And then I can split this fraction up, combine the u to the 1/2 with each of those terms. Questions? Agree? Then you got power rule, and then you're going to substitute back your 1/2 x plus 1 for every u. Okay, there's an important announcement I forgot. We have reserved a room for a study session tomorrow from 3 to 4:30. 3 to 4:30 Thursday, open study session. Both TAs will be there to support you in your studying, practicing, getting ready for the test. That is in LSE, but I don't know the room number off the top of my head, so I'm going to post an announcement on Canvas. The L Life Sciences E building. 3 to 4:30 Thursday, open study session. TAs will be there. I will keep the video running, and I will start this one. If you want to stick around for a minute and watch me do it, or check out the video. It'll be on the video, this last one. Hi.
Would you recommend doing these for like trig substitution?
For what now?
Like trig substitutions?
So I was teaching you how to do them without this. I taught you how to do the trig ones without. Oh, trig substitution. We don't do that. We didn't do that method at all. That's using the triangle trig. We didn't even do that. So that's not. You're not responsible for that. 1/7 over 1/7. Is that what you're asking?
Like -7 out front in the integral, so that it could just be R10.
But you can't. No, it's plus. It's plus. You can't. Plus. It's not.
The du is negative, so like in the fraction we consider negative. So I was wondering, like I got to your point.
You can't pull out a 7 to make this a 1. You need to multiply that by 1/7. This is added in the denominator. You can't just rip a 7 out of a denominator like that.
Well, I was thinking multiply by 7 over 1.
That's kind of what I'm doing. So what you need to make this 1. So you need u squared plus 7.
Yeah.
You need to multiply the top and bottom by 1/7. What's that? No, it's multiplying by 1. You can't just multiply a fraction by 7 and then changes the fraction. So this is 1/7 over 1/7. But then you need to know this. Then you're talking about this. You know that? You know that integral? That's what you're saying. Yeah, so you have that rule memorized. That not everyone does. So I'm trying to make this a 1. So it's about the same thing. So I want to make this a 1, then I know it's arctangent. If it's something else, yeah, there's a formula to do with arctangent. Yeah, and if you know that, that's fine. But wait, this isn't right. This is a 7, right? This is 7. Okay. There we go. So that does it? That does it? Which is 1 over radical 7 all squared, right? That. But then by the chain rule, I'm going to need square root of 7 here. Does that fit your formula that you were going to do now?